Hey, welcome back. This is 12.5. Now we're actually going to begin modeling or working with exponential models. So first, what are the models? We'll describe them with exponential functions, in particular f of t equals a sub 0 e to the kt, where that a sub 0 thing, this whole thing right here is just a constant, okay, like a number like 50 or 23.8, something like that. Okay. We can also write it as a equals a sub 0 e to the kt. Okay. Yeah, so a sub 0 again, a sub 0 is going to be basically your initial value, initial population, whatever. It could be an initial amount, like you have 20 grams of radioactive material, something like that. Then there's two versions, one where the growth value k is greater than 0 or the growth value k is less than 0. If it's greater than 0, you have exponential growth, okay? And we don't worry about the negative side here. We just want the positive, the first quadrant, okay? So it'll look like this, and this is exponential growth. And then the other case, when k is less than 0, it's just going towards 0, right? So this is exponential decay. It's basically your same old exponential functions. If you remember, e to the x looks like this, and e to the negative x would be that same thing, kind of rotated around the y-axis, look like that. Except we've chopped off this part of it, right? And then we multiplied it by a sub 0. So now the y-intercept is no longer at 0, 1. And in our case, it's at 0, a sub 0. Okay, so these points are at 0, a sub 0. Okay. Okay, so there's exponential growth, and you use that to model population growth or bacteria growth. Exponential decay, you mainly use that for radioactive stuff. Okay, and we'll see the carbon dating thing, I'm sure. All right, so let's look at like the first problem in the homework, if I can find it. They give you an exponential model, a equals 645.3 e to the 0.013 t. The population, this thing describes the population A of a country in millions. So A is the population in millions of some country. T years after 2003. So T is going to be the number of years after 2003. Okay. Alrighty then. So I want to know what's the population in 2003. In other words, when T is 0. Okay. So all right, A of 0 is going to be 645.3 e to the 0.013 times 0 is just 0. Okay, e to the 0. And then anything to the 0th power is just 1. So I have 645 million people in the country in 2003. Okay, so one kind of way, a shortcut, is just to kind of say, here, this is it. This is your initial population. And if you look back at the formula when I first introduced it, that's the way I introduced it. A sub 0 is the initial population. But if you kind of forget that, you can always just substitute in 0 for t, and it'll tell you that a sub 0 anyways. Okay. Let's look at another one. So question 2. The exponential models given to the right here, there's 4 of them, describe the population of a country in terms of millions, t years after 2006. Which one has the greatest growth rate? So in this case, you're looking at the thing in the exponents. So for country 1, it's a equals 26.6 e to the 0.029 t. So the value we're looking at now is this thing. That is the k value. And we want to find the country with the biggest k value. Okay. The second country has negative k value, so that's their population is decreasing. The third country positive, but it's only 0.013, which is less than country 1. The fourth country, 0.003, is less than country 1 as well. So the country with the greatest growth rate then is country 1. So country 1 has the greatest growth. And for every year, we'll say that that describes the increase of the population. So if you multiply that by 100, you would get 2.9% for our increase. Okay. Okay. More sort of. Okay, so this question 3 is kind of the reverse of the problem. So they're going to give you. Okay, so let's see what they say. We lost it. Where are you? Okay, so the exponential model A equals 402.5 e to the 0.027 t describes a population in millions t years after 2003. Use the model to determine when the population will be 881 million. Okay, so just remember, t is the number of years after 2003. Okay, so how do I figure out when the country will have 881 million people in it? Well, what you do then is let A equal 881 and solve for t. Okay. So what this becomes then is an exponential equation. To solve this, you first need to isolate the exponential part. So get that by itself by dividing by the 402.5. Then take the natural log on both sides. On the left here, the ln and the e kind of cancel each other out, and you're just left at the 0.027t. On the right, I get the ln of 881 all over 402.5. Divide by the 0.027, and t will equal ln of 881 all over 402.5 divided by 0.027. Okay, so I'll just go the Wolfram. 881 divided by 402.5 divided by 0.027. I put too many parentheses in there or something. Didn't like it. So getting approximately 29.0134-ish. They're probably going to want you to round to the nearest year. And we're talking years after 2003, so you need to round to the nearest year. So this will be about 29 years. So it'll be 2003 plus 29 is 2032. Yay. All right, sort of, I guess probably more of the same here. Let's move ahead of this one. I mean, we could do it. Sure, let's go ahead and do it. So in 2000, the population of a country that was approximately 5.63 million by 2040 is projected to grow to 2 million. Use the exponential growth model, in which t is the number of years after 2000 and a sub 0 is in millions, to find the exponential growth function that models the data. Okay, so problem 4. Right, so my model A equals a sub 0 e to the kt. A is population in millions, and t is the number of years after the year 2000. So I'm just kind of getting my bearings by writing down all the information. They say the population of the country was 5.63 in 2040. Okay, so you could think of that as an ordered pair. 2040 is 40, that's t is 40, and then the other point would be 5.63. Whoops, I read that wrong. Sorry, and it says in the year 2000 the population of the country was 5.63 million. So when t was 0, you get 5.63 million. And then by 2040, which is t is 40, it's expected to grow to 9 million. Okay, so for part A, what they want you to do is use that information to kind of fill in the blanks in your formula. You need a sub 0 and you need k, and then you'll be able to use that formula to do whatever they want you to do. Okay, so a sub 0, again, from above, we know that's just 5.63 because that's the initial value. Then we could use the second ordered pair to solve for k. All right, so I'm going to put 40 in for t and 9 in for a. So I end up with 40k. Then it's an exponential function, equation rather, and I want to solve for, first solve for the exponential part. So I have e to the 40k equals 9 divided by 5.63. Then I'm going to take the ln on both sides. Okay, so I'll have 40k equals ln of 9 all over 5.63. Then divide by 40. So get ln of 9 all over 5.63 all over 40. Usually if they don't say anything, I'll take this out to 4 decimals. And the work here, though, in part A, they say round the 2 decimals as needed. Okay, so this time I'm just going to round to 2 decimals, but if they don't say, round out the 4 decimals at least. Later in math, I'll just keep it as it's written so I can avoid any approximation errors. But for now, we're going to go to 2 decimals. Okay, so it's 0.01 for k, and so I could rewrite my model now as a equals 5.63 e to the 0.01 t. And I think the book asks for it, or the homework asks for it, and then you could put it in and make sure it's right before you go on. All right, so yeah, there it is. When will the population will be 16 million in what year? So part B, now you take this equation, this a equals 5.63 e to the 0.01 t, and use it to answer the questions. So 16, they want to know when the population will be 16 million. So you put in 16 for A, and you want to solve for t. Okay, so again, it's an exponential equation. I want to solve for the exponent part first, the exponential part first. E to the 0.01 t is equal to 16 divided by 5.63. ln on both sides. I get 0.01 t is the ln of 16 all over 5.63. Divide both sides by 0.01. T will equal ln of 16 all over 5.63 all over 0.01. Put that in your calculator. It's 104.45 if they want 2 decimals. I don't know how many decimals they want. Let me see. Round to the nearest year. Okay, so 104 years. Remember, this is representing a number of years after the year 2000. So it'll happen in 2104. And then you just plug that into the computer and let it do its thing. Okay, great. As usual, I've removed some of this. These are kind of weird. These fill in the chart problems, so I just want to do one of those to make sure we're all on the same page. It's question 6. Kind of fill in the chart. They tell you that the population in 2006 is 36.6 million. projected population in 2045 is 56.2 million, and they want you to first find, well, I guess only just find the growth rate, k. All right. Okay, so you can say that t represents the number of years after 2006, right? Which would mean that your a sub 0 is the 36.6. So you could write your initial equation as a equals 36.6 e to the kt. Then so we use this part. Now use this part to solve for k. So you got to be a little bit careful here, right? Because what is 2045 in terms of t? 2006, 3, 15, 9, 3, it's 39. T is 39 in that case. So plugging in 56.2 for A, I get 36.6 e to the 39k, and then I could solve that for k. So it's e to the 39k equals 56.2 all over 36.6, ln on both sides. You end up with 39k equals ln of 56.2 all over 36.6. So k equals ln of 56.2 all over 36.6 all over 39. We need 4 decimals. So n of 56.2 divided by 36.6 divided by 39. They want 4 decimals, so this will be 0.0123, and of course 4 is a 9, and then they got another 9 there, so you're just, you're adding 1 to this position. So 0 carry the 1 is 1, 1, 0.0. And as usual, I have to find what the homework is. Okay, so 0.0110. Yay. Alrighty then. Let's see. Okay, so now question 8 takes us to radioactive decay problems, and in particular here, it's a carbon. This is one of the carbon dating problems, so we want to take a look at that. I guess so. Sort of 2 is carbon dating. Okay, in order to work with this carbon dating, you need to kind of know the half-life of carbon. I guess they kind of skirted the issue in this problem. They kind of give you the formula. Let me find one that maybe doesn't give you the formula. So in the book, what they're going to do is kind of generate the formula for you. But in general, in a real problem, you would have to kind of figure out the formula yourself using the half-life. Okay, so maybe I should hit example 2 here. Okay. Basically, what's happening is they know how long it takes for carbon-14 to decay, so they kind of do a comparison between carbon-14 in the atmosphere and then carbon-14 in the thing that died. So once the thing dies, the carbon-14 will start to decay. All right, and they can compare that to carbon-14 and things that haven't died, and kind of figure out how long the object has been kind of quote-unquote dead. All right, so example 2, what they're doing is saying, and I mean, I'm no expert on half-life. All I know about half-life is from what I've read. So maybe our next example involves exponential decay and is used in determining the age of fossils and artifacts. The method is based on considering the percentage of carbon-14 remaining in the fossil. Yeah, so that's what I was talking about. Once the fossil is buried or it dies, the carbon-14 will stop will start to decay. That's what I want to say. So once it dies, it'll start to decay, like get old, you know. And they'll sort of look at the amount of carbon-14 left in the fossil or the artifact. Carbon-14, they say, decays exponentially with a half-life of approximately 5,715 years. The half-life of the substance is the time required for half of the given sample to degenerate. Thus, 5,715 years after a given amount of carbon-14 will have decayed to half the original amount. Carbon dating is useful. So they don't really explain how it works, but I believe it's comparison between the carbon-14 and the atmosphere or something, and the carbon-14 and the object that has started to decay. I think that has something to do with it. All right, so anyways, let's take a look. Example 2. Use the fact that after 5,715 years, a given amount of carbon-14. So use the half-life, okay? So it says the half-life of carbon-14 is 5,715 years. So what does that mean? Well, if you go to your model for exponential decay, which is the same as the exponential growth model, the half-life means that in this time period, so you plug in 5,715 for t, and you have 5,715 k, and in that time period, you're only going to have half the original amount left. So what is the original amount? 1/2 of a sub 0. A sub 0 is the original amount, right? So from here, you can solve for k, because you've assumed the original amount is greater than 0. So you can divide both sides by that constant a sub 0. So you get 1/2 equals e to the 5,715k, and here you only have one variable, so you can solve for it. You just take the ln on both sides, flip the sides, you get 5,715k equals the ln of 1/2, and then divide by 5,715, so you get the ln of 1/2 over 5,715, right? So our model then, based off just this half-life fact, which is what happens in a lot of these story problems, you'll have a equals e to the ln of 1/2 all over 5,715t. Okay, and they probably want a decimal approximation, which I usually don't do. Yeah, so they give it to you in the book, negative 0.000121. Okay, so this will be approximately e to the negative 0.000121 t. Okay. Whoops. A equals a sub 0. Yeah, so a sub 0. There it is. Okay. And they give you that model there in the book. I'm trying to highlight it, but it's not letting me. It's right there. Okay. Okay. So we're able to construct our formula based off that. Then part B, in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab Bedouin herdsman. Analysis indicated that scroll wrappings contain 76% of the original, and I know that's by an Arab, I guess that's a location. I thought maybe that was his name. I am so sorry. By some Arab herdsman. Analysis indicated that the scroll wrappings contain 76% of the original carbon-14. Okay, so that quite literally, whenever you see the word of, that means to multiply. So 76% of the original amount is 0.76 times a sub 0. Okay. And then on the other side, we could put a sub 0 e to the negative 0.000121 t and solve for t. Right? Because all we were doing is basically using our new formula, which is a equals a sub 0 e to the negative 0.000121 t, and plugging in this fact that they found by looking at the Dead Sea Scrolls. They noted that 76% of the original carbon remained. Okay. So you just sub in 70.76 times a sub 0 for a, and then solve for t. Okay. So it's kind of using this formula. All right, so first divide both sides by a sub 0. Get 0.76 equals e to the negative 0.000121 t. Take the ln on both sides. So you get switching sides, negative 0.000121 t equals the ln of 0.76. And then solve for t. So t would be ln of 0.76 negative divided by the 0.000121. Okay, and we want to get the age then, so you just supposedly just plug that in, and that would be your age. So negative ln of 0.76 divided by 0.000121. You're getting about 2,200 years old, 2,268 years old for the Dead Sea Scrolls. Okay. You do the same process in other problems. So getting back to the homework then, and looking at what you have there. You know, in this problem 9, you're given a half-life and you're able to get the formula, but problem 8 here, they give you the formula in this one. So let's look at number 8, I guess. An artifact originally had 16 grams of carbon-14. The decay model, then, they just give it to you, right? So it's a little easier in this one. Describes the amount of carbon-14. Use the model to determine how many grams will be present in that's just a plug and chug. So you just plug 7,705 into the t value. So that one's pretty easy. Just plug and chug. This one, a little more work, right? But not really. You could do this one kind of, you can cheat your way through this one. So the half-life of unobtainium 37 is 20 seconds. So half-life is 20 seconds. So you're beginning with 48 grams. 48 grams. So how many are present after 20 seconds? Well, because it's a half-life, you know that it must be 24, because in 20 seconds half the original amount is gone. So you just have 24. How many there after 40 seconds? So you just divide that in half again, so that would be 12, etc. 60 seconds, so that's another 20 seconds, so you get 6. Okay, so you kind of see that you don't always have to go through the hard work. This is another carbon 14, so you're just putting 0.33 a sub 0 in for a. Okay, this is one where you're figuring out that you have to figure out the k value, right? Let me look at, I sort of found 29. I want to look at 29. Okay. 27. I want to look at this one. Okay. Let's make this one the video quiz as well. Let me plug that into my notes. This will be the last video quiz for chapter 12. Video quiz number 15 from, this is problem 15 from my math lab. Okay, so I'll put that in my notes. Video quiz, video quiz, video quiz. All right, so you got your exponential decay model. In this problem, though, they're not going to give you the k value, right? But they do tell you the half-life. The half-life is 23 years. How long does it take for the substance to decay to 73% of its original amount? So 0.73 times a sub 0. Okay, so anyways, I need to find k, right? So I can do that by noting that after 23 years, so if I plug in 23 for t, 1/2 of the original amount, a sub 0, will be left. Okay, so you just divide both sides by a sub 0. 1/2 equals e to the 23k. Take ln on both sides. Get ln of 1/2 equals 23k. Divide by 23. So get ln of 1/2 divided by 23. Okay, it doesn't, I guess it does tell you at the end to round to 1 decimal, but if you look at this number, there's no way you can round it to 1 decimal because it would be 0. Sorry. So just a commentary on the state of affairs in my math lab. Rounding that to, well, I guess you could round that to 2 decimals. It seems like there's a problem I did, and you couldn't really round it because if you did, it would just be equal to 0. See, round to 1 decimal. If you rounded that to 1 decimal, it would be 0. So, no, it's not round to 1 decimal. It would go to the 4. Okay, so negative 0.0301. Okay, all right, so let's rewrite our equation now. A equals a sub 0 e to the negative 0.0301 t. I mean, worst comes to worst, you can always just put this actual thing in here. All right. Anyways, what do we want to do now? We want to solve. How long does it take for a certain amount of it to go away, right? We only want 73% of the original amount left. So you go 0.73 of means to multiply times a sub 0 equals a sub 0 e to the negative 0.0301 t. Divide both sides by a sub 0. 0.73 equals e to negative 0.0301 t. ln on both sides. Okay. So you get flipping sides, negative 0.0301 t equals ln of 0.73. Divide both sides by negative 0.0301. So t is negative ln of 0.73 all over 0.0301. Let's see what that is. Negative ln of 0.73 divided by 0.0301, which is 10.4 something. Let's see how many decimals I think they said one decimal, right? So this should be 10.5. Yeah, which is what I wrote. So 10.5, great. So that was your video quiz for the day. Let's see what else business we have in store for you. Some more stuff. There's doubling time in addition to half-life. So problem 18, the growth model A equals 5.1 e to the 0.06 t. And then they're telling you the doubling time if you know the k value. So another way to figure that out, instead of half-life, doubling means that it's the time it takes the initial population, which in this case is 5.1, to be multiplied by 2, right? To be twice as much. So you can solve for t in this case. To first divide by 5.1, so you get 2 equals e to the 0.06 t. Then take ln on both sides. And you get ln of 2 equals 0.06 t. Dividing by 0.06, you get ln of 2 all over 0.06, right? So if you look at the formula they give you, that's the formula, ln of 2 over that thing. Then that's also the growth rate of the country, and then you have to convert it to a percent. So ln of 2 divided by 0.06. I don't know how many decimals they wanted. 11.55. We wanted the k. They wanted the growth rate, right? So the growth rate would be, well, you already know the growth rate. No, they wanted the doubling time. Sorry. So yeah, it's 11.55 whatevers. years. The country's growth rate is, well, it's sitting right there. It's 6, for heaven's sakes. You just look at the exponent. How long will it take for the country to double its population? That's what I just found. So 11 nearest whole number, so 12. 12 whatever time units, I guess years. Okay. All right, so doubling time is in there. I need to get rid of these scatter plot problems. I'll go back there and do that. Okay, everyone, so this last topic is kind of off topic, but you kind of need to be able to do it later on for certain procedures, and if you have the misfortune of taking calculus. I need to rewrite an exponential as an exponential with base e. Okay, so I don't know what to title this. I'll just title it base e. Okay. Okay, so if you have a to the x, you can rewrite it as e to the ln of a to the x, because e and the ln are inverse functions, so they'd kind of cross each other out, and you just have a to the x. You're not going to leave it there. What you're going to do is use the product rule, the power rule, excuse me, then to bring the x in front like that. Okay, so this is going to be e to the x ln of a, and that's just how it works. All right, so for example, question 22, we want to rewrite y equals 106 times 3.9 to the x. It's this part you're rewriting with the exponential in the base. So you would have y equals 106 e to the ln of 3.9 to the x, and then you use the power rule to rewrite that as 106 e to the x ln of 3.9. Okay. And then they want you to round the answer. Yeah. Okay. Same deal here, same kind of problem, and I guess that's about it then. Okay, so we'll leave you there. As usual, thank you for watching, and I'll see you next time.